somebody has a pointer, so I'm going to go back and forth. I just would like to mention Dr. Fan Yang, a colleague of mine, and he is in my session too. And this work that I'm going to present is one of the projects that we're working on in our session too. And it basically deals with reflect array and transmit array antennas, and I'm going to explain why we deal with this. Before I start, on the left, the engineering building, on the right is a research building in which we have all our research equipment. And let me give you a very brief introduction on large antennas, and specifically for space applications. We see here if we have a satellite and has to communicate with the Earth and has to capture some images or soil moisture or any other surface profile. It has to go through snow, sun, rain, all kind of climates, variations. And for this, we really need to have antennas with some specification like frequencies that goes all the way from 1 to 200 gigahertz, resolution from 3 to 50 kilometer, and the swath itself most likely is over 100 kilometer, and obviously the costs are in billions. And here is just one spaceship, and you can see the largest object on that spaceship is a parabolic reflector antenna that provides these capabilities. I just would like to highlight this so that I can give you the classification between different antenna in terms of their gain. If we are talking about low gain antenna, we are talking about antennas that are wires or monopoles or batch antennas, medium gain antenna that goes all the way to 20 dBi. I means isotropic, that's basically cords and small kind of antennas. We are interested in antennas that have high gain, and most of the times you are parabolic reflector antenna, big shape, pyramid structure with a feed either at the focus or another sub-reflector here, and the feed at the center of the reflector itself. Is a very clumsy structure, very efficient in terms of gain, but it's not very practical in many applications. You can see some of those reflector antennas are here made out of mesh, made as an umbrella that you can fold it out when you launch it in space, and you will. Maybe it will take 3 seconds to. Okay, so how do we get high gain antenna? One way to do it is to use patch antennas, and you put them in array structures. And if we can have this panel composed of so many antennas, you can count here 4 times how many here, and then you stamp all those patches together. You can end up with large aperture, and this large aperture is going to give us a high gain antenna. But the cost here and the trouble here is basically the feeding network. We need to feed each one of those patches with a network that looks like this, which is very, very complicated to do, and most of the time you lose efficiency and you lose gain from the feeding structure itself. Okay, so the way to do it is, instead of having this big parabolic reflector antenna, even if we go for batch antenna arrays, the way to do it is to use what we call it reflectarray. And what you see here is one of the reflectarrays that we have designed and fabricated and tested in our labs. And I'm going to give you the good features about this design, and also the less capabilities that we have from this planar structure, and how I'm trying to overcome those less capability related to the parabolic reflector antenna. For example, we would like to create multi-beam, contour beam, things that we may not be able to do it with the parabolic reflector antenna, and I'm going to show you the techniques on how to do these things. So how to analyze this, I'm going to go quickly, and I intended not to bring here so many equations, but the procedure for analysis, design, and verification are basically sketched out here in certain items that we have to follow. The most important item is the element analysis, and when you look at this shape here, it's basically constructed from small elements, and that's basically the element analysis. We do some synthesis for this element, and after we decide which element to use, we're going to start designing the reflectarray itself as a whole unit, and then we test it and verify the design. So in another way we can look at this, before we started this project, we looked at this in 3 different ways. We need to design our analysis tool, or make our analysis tool, or use some analysis tool that we think is going to work. We need to provide some optimization tools, and we need to fabricate and measure and verify our results. What you see here, some methods that we have used. I'm sure not everyone is familiar with all these, so I don't want to go through all these details, but once we figure out the tools that we can use, we can study efficiency analysis and the phase error analysis. I'm going to stress on the phase analysis to show you why we are doing this. We can also do some optimization, alternative original method we started with, and then part with one optimization. And fabrication, we did it in the lab, testing in the lab, and I'm going to show you later on some sample results. Here, for example, what you see here, those are the 3 categories again, and our objective out of those 3 categories to create some features in the reflector array that does not exist in the parabolic reflector itself, like broadband. Well, actually, broadband exists in the parabolic reflector, but by nature, the reflector array is narrow band, so we would like to increase the band of it. Multi-beam, we can create it with Reflectarray. Beam scanning, we can create it with Reflectarray. And we would like to go all the way to the infrared and solar cell applications that we are working with right now. We use the Reflectarray and transmit array to enhance the solar cell capabilities. What you see here, some multi-beam radiation pattern from reflector arrays that we designed. You can see beam scanning, and you can see a full simulation for the entire reflector array in one full electromagnetic full domain simulation. So the process is basically goes through element design through certain steps, and then system design, and in a little bit more natural way for such kind of design, which looks complicated, but really this is really what we have to do. Again, we start with element design, and we go from here until we reach a specific design. I'm going to skip this one because I have another topic I have to talk about it as well, so I'm going to go quickly. And because we have a nested procedure like this, we created a graphical user interface to simplify the analysis for those who are coming into the subject and don't have that experience. And just to mention that the one who created this interface is an undergraduate student working in the lab. He takes bits and pieces from our graduate students and put them together and create this interface. This is an image of the near field system. It's basically one reflector array here that we designed, excited by horn. Signal reflects back. This probe here for the scanning system, basically a square area, goes this way, and then we change the polarization of the we scan this way and capture the field, and then take this field from the near field to the far field and predict the gain and radiation pattern of that antenna. The key point in this design starts with the element. Imagine that we have a square area that we're going to create a reflector array on it. You can see here different elements of different sizes. The reason for this, because when the wave hits this point, it needs to reflect back with a specific phase reflection here. The reflection coefficient here has amplitude and phase, and we control the phase at each point on the surface in order to collect the reflected energy in one direction, and that's how we collect the energy in one beam direction to increase the gain. So this is the whole idea. How do we change the phase? Is basically changing the dimension of the element, or putting those tails or delay lines with different lenses to change the phase at each position, or do some sort of rotation to be able to change the phase. So the key point is to start with one element, analyze it completely, figure out the phase of it or the phase variation, and use this element for your design. Here are some samples of plane cuts of the radiation pattern using 2 different techniques here, and one technique and full wave simulation. And from this side here, you can predict the aperture field, which is not very time consuming, can predict the far field accurately, and we can continue using it. Here is an image of a reflector array. This is a distribution of the elements that gives us the right phase. This is how it's being simulated fully in one electromagnetic solver. This reflector array has about 440 elements, works in the Ka band, and this is basically the prototype that's being fabricated. Here is one of the things that we have finished about a year ago, and that's very hard. Okay, I'll try. But the key point here is that to achieve something that's not been achieved before. People, when they design a reflectarrays, they design it for one frequency. They need a second frequency to work on, they add another layer. A third frequency, they put a third layer. That's very costly and very cumbersome. Here we have designed one layer reflectarray supporting three frequencies. These crosses, red crosses, support 7.1 gigahertz. Those square with slots supports 8.4 gigahertz, and small circles with the opening supports PA band for 32 gigahertz. So we managed to be able to design and simulate and fabricate, and this is the final product here. If you take a closer look, you can see the crosses, the squares, and the circles, and operating at those three bands. These are the number of elements for each band, and these are the gains of the same gain for those three frequencies. All of them are about 25 dBi. Different other reflectarrays that we're working with, and the fabrication comes using this milling machine, which I have seen here in at least 2 universities, so it is not very hard for universities to get into this business and try to analyze and simulate and fabricate. Testing may be hard, but at least you can fabricate. And here I would like to show you that if you use spacing between the elements that's equal lambda by 3, lambda is the wavelength, you can improve the bandwidth, which is one of the drawbacks of the planar reflectarray. If you use multi-layer, you can increase the phase, and eventually you can increase your gain bandwidth. And here is another topic that we achieved, is that if you have one reflectarray with one main beam, how can we create 4 beams out of one design? We used 2 different techniques, produced those 2 patterns. We were not satisfied with them. We did some optimization, and you can see clearly that those 4 beams are much better, much more concentrated. Side loop levels are less, so most of the energy are going to the beams that we intend to have rather than the surrounding beams. This is a fabricated reflectarray under test, and this is a measured pattern, compares very well with this simulated pattern. Let me jump here into another topic that we did, is that you can even control the amplitude and the position of the beam. So here we designed 4 beams, each one of them with certain intensity or certain amplitude at different position. A scanning capability is basically, you can see some scanning capability from -30 to +60, 60-degree scanning capability with the reflectarray. We use also conformal reflectarrays that we designed recently, so that we can conform it into bodies, and this will give us much more capabilities, much more scanning capabilities. Okay, so I'm going to switch to another subject. The next one will be very quickly, which is RFID, and also the research projects that we are working on it for over 3 years right now, and mainly with collaboration with Cambridge University of Technology, with which I spent 1 semester sabbatical. In this image here, you can see OLMIS, our university is called the University of Mississippi, but people call it OLMIS, and you can see a chip here that's basically an RFID tag. Okay, so what almost everyone knows right now what's RFID. It's basically a reader and a tag. You can put the tag in many things. Here is one familiar commercial tag, and you basically put these tags with items, and you would like to be able to figure out where those items will track them or expect them to be certain where, or if they are there or not. Here are an image of some of the readers, some of the commercial tags, and more commercial tags. But the top hand here, I'd like to show you that there are 3 different frequency bands for Europe, Japan, and the United States. But if you design a tag that goes from 860 to 960, it will cover the 3 different systems. Now, RFID can be used in many applications. You can see it through traveling, banking, post office, libraries, airports, and luggage. You can also see it in retail stores, in transportation, and civil defense. And here is one thing that I would like to show you. What we are doing right now is putting sensor inside the tag itself, inside the RFID tag. So it's not only you can read it and figure out where the item is, where the tag is connected to, but you can sense some other features. For example, this one here is specifically designed to be able to sense temperature. And we can have the precision tag, the chip, and then the underlying line, and under it a pocket that's filled with liquid material that senses temperature. Okay, here is, I'm almost done. Here is another more advanced sensor that basically shows you the area in which we sense the temperature. Here is our measurement next to a reference sensor. And basically the performance that you see it here at different temperature gives you the minimum point at which we can figure out the shift in frequency is correlated to the temperature where the tag is. This design is based on one board, one chip, and we came up with a new design. Even this result is not published yet, in which we have two boards. And the two boards will give us much more accuracy, much more capabilities in terms of having the reference tag, not to be a separate tag and not to be a separate identity. So it's one unit, one tag that has two boards. One is a sensing board and one is a reference board. And this is the performance of the reference board, doesn't change with temperature, and this is the performance of the sensing board. Here is another sensor that we also designed. This is the front and this is the back of it. And this is a humidity sensor. And you can see the change of the frequency based on the humidity. And the humidity is represented in terms of the constant of the material that's basically changes based on the humidity of the environment. With this also I would like to show you that we have created a software package that will allow us to analyze antennas. And this software package is very fast based on finite difference time domain. And it's fast because we use the GPU or graphic processing unit to use all the sensors and all the processors in the graphic processing unit to speed up the calculation. Here is an image of a circular regularized tags. And here is also something I would like to show you, which is basically one of the new things that we're doing is to print tags on Kapton material. These are inkjet printed RFID tags. These are two different tags that are being designed relative to a reference tag. And most recently we created composition of material that's very flexible, use inkjet printing on it, and we create something very flexible, very and you can put another layer on top of it, sealed, and you don't know that there is something inside. And that's basically a very well designed tag and behaves very well. Small tag also that sits on this flexible material. And just to show you how we test all these things, we have a cabinet here that has a rotator here and antenna here, and outside a tag performance device. And this entire unit is nothing more than $30,000 that you can have it to be able to use to predict and to measure all these capabilities. So here,
trying to launch this presentation, you can take one or two questions. Okay, right.
Sensors data and the extra added the feature to the RFID.
yes.
What uses do we look out for?
The humidity sensor, obviously for humidity, temperature sensor, you can use it.
No, I understand, but would it be something like if the humidity increases or something to send a signal to turn off a certain feature?
Yes. When you read it, when the tag is passive, all what I presented here are passive tags, so they don't require any battery. So when you read it with the reader, you are gonna see a shift in frequencies that gives you an indication about the humidity of the medium that the tag. The same thing for the